Hello dear students, welcome you all. This is Anirudh Singh Rathore and we are going to discuss types of failure. So in this class we are going to discuss only one topic, that is types of failure. So let's begin. See, there are various types of materials. Basically we can say there are two types of materials. One is ductile material and another is brittle material. So I've already explained you what are ductile materials and what are brittle materials, but let us have a recap. Ductile materials are the materials which undergo large strain before failure. So whenever we are putting some tensile test before failure, just at the time of failure, we'll observe that they have undergone large plastic strains. Okay, brittle material are such that they fail suddenly, they start cracking without any appreciable strain. Okay, for example, there is rock. If you put tension test on a rock, it will not undergo any changes in its dimension before failure. Whereas if you test for mild steel, if you pull mild steel, it will keep on stretching and it will undergo large plastic strain before failure, right? So ductile material undergo large strain before failure, brittle material, they suddenly fail. Okay, so these are the two types of materials. Now we'll see in types of failure that we'll apply different types of loading on ductile materials, we'll apply different types of loading on brittle materials, and we will see how these two types of materials respond to these different loadings. Okay, so what are the different types of loadings we are having? We are having tension loading, we are having compressive loading, and we are having torsion loading. So tension loading, as you can understand, we are applying tension forces. Compression loading, we are compressing the material, and torsion, we are doing torsion test. Okay, now these three types of loading will be done on both type of materials, that is on ductile material and brittle material, ductile material, brittle material, ductile material, brittle material. So these three types of loading on each of the two materials will give us 6 cases. So in the types of failure we have these 6 cases, and we have to study in each type of loading what kind of failure we will observe. Okay, so let us, before going to apply these forces, these types of loadings on these materials, let us see how ductile materials, what is the, how strong they are in compression, how strong they are in tension, and so on. So what is the relative strengths in tension, compression, and shear, and what is the relative strength of brittle material in tension, compression, and shear? Okay, so if we talk about brittle material will be strongest in compression. Brittle material will be strongest in compression. So compressive strength of brittle material will be highest. Okay, after compressive strength, brittle material will be strongest in tension. Okay, so their tensile strength will be little bit less than compressive strength, but their shear strength will be smallest. Okay, so ductile materials are weakest in shear strength. Okay, for example, we have a ductile material, mild steel. So mild steel is strongest in compression. If I say what is the compressive strength of mild steel, it will be around 263 megapascal for mild steel. For mild steel, compressive strength will be 263 megapascal, and tensile strength will be just little bit less than that. It will be around 250 megapascal. Okay, but their shear strength will be much lesser. Okay, so this will be the order of their strength in different types of loading. Okay, now let us see what is the order of strength of brittle materials. So brittle materials are also strongest in compression. Brittle materials are also strongest in compression. So compressive strength of brittle materials is also highest. Okay, but these two will interchange. Okay, their shear strength will be much lesser than the compressive strength, and their tensile strength is even lesser. Okay, tensile strength is even lesser than the shear strength. Now if I take any example of brittle material, so brittle material example is cast iron. So if I compare the compressive strength of cast iron and tensile strength of cast iron, so compressive strength is much higher it will be around 100 megapascal, sorry, 400 megapascal. So compressive strength of cast iron is around 400 megapascal, but tensile strength is around 100 megapascal. So you can see that cast iron, or if I take any brittle material, so brittle materials compressive strength will be much higher as compared to the tensile strength. In case of cast iron, we can say that compressive strength is around 4 times its tensile strength, right? Whereas in case of ductile material, there is not much difference in the compressive and tensile strengths, right? So although compressive strength is higher than the tensile strength, they are almost equal, okay? But in case of brittle material, compressive strength is much higher as compared to the tensile strength, right? Okay, so now we have seen that what is the ratio of strength, or we can say what is the order of their strengths. Let us see how they will fail in when we apply these types of loadings. Okay, so first of all, let us see tension failure in ductile material. So I have a ductile material and I will apply gradually applied tension loading. So when I apply gradually applied tension loading, since this is ductile material, it will undergo large strains. Okay, so it will undergo stretching, it will start stretching, and before failure it will undergo large strains. And in the when I was teaching you stress strain curve of mild steel, I have taught you that these mild steel, stress strain curve of mild steel, the fracture will happen as a cup cone failure. Okay, so necking region I have already told you. So what happens, suppose this was the original specimen, and on this original specimen, let us say I have applied a tension loading, let us say T, and I am slowly increasing the value of this load T, tension load T. I am increasing the value. Okay, so what will happen, that this will start elongating and lateral dimensions will start reducing, and length will start increasing. Okay, now after some time, what will happen, after some time, that after too much strain, what will happen, along the weakest plane, the area will start suddenly decreasing. Okay, suddenly the area of cross section will start decreasing, and this type of formation will occur. This type of formation is called as necking. Okay, and at 45-degree planes, to the tension loading, we will observe that there is the maximum shear. Okay, maximum shear, and because of that shear at 45-degree plane, there will be a failure. This is called as cup cone failure. So the tension test specimen will look something like this. At one portion, there will be cup, and at other portion there will be cone like this. Okay, cup cone failure, and angle will be 45-degree failure. Okay, so this angle will be at 45-degree, because when I apply tension loading, uniaxial tension loading, okay, so because of that tension loading, there will be a maximum shear stress at 45-degree angle. Okay, so it will fail at 45-degree angle, right, like this. Okay, clear? Okay, so let us write down some points. Failure plane is at 45-degree. So failure plane is at 45-degree to the applied load, Failure is because of shear. Okay, failure is because of shear. So failure, so although we have applied tension loading, but the failure is happening because of shear. Okay, so failure is because of shear, and this failure is called as cup cone failure. Okay, here we are seeing the formation of a cone, and here we are seeing the formation of a cup. Okay, so this is called as cup cone failure. Cup cone failure, right? So this type of failure is called as cup cone failure. This type of failure is called as cup cone failure, right? Okay. So if I want to see the specimen, failure specimen, this specimen will look like this. So here we are seeing the formation of a cup, and here we are seeing the formation of a cone. So this failure will be called as cup cone failure. Okay. So next, let us move on to the next case. Let us apply tension load on brittle material. Now, since this is a brittle material, in brittle material, you know that there will be not much elongation at the time of failure. And also tell me, here the failure was because of shear. Why shear? Because ductile material is weakest in shear. So whatever the ductile material is weakest in, it will fail in that mode of failure, right? Okay. Now, can you tell me what is the weakest strength of brittle material? So brittle material is weakest in tension, and we are applying the tension. So you can easily observe that at 90 degree, there will be maximum tensile stresses, and this is also weakest in tension. So when tensile stresses are maximum at 90 degree only, and this is weakest in tension, it will fail at 90 degree. So failure plane will be at 90 degree to the applied loading, or we can say to the longitudinal axis. So failure plane will be at 90 degree. Failure plane will be because of principal tension, and there will be a rough surface, little bit rough surface will be there, not very smooth surface. Okay. So here we can write down the points. Failure plane is at 90 degree. Failure plane is at 90 degree. Next point, failure is due to principal tension. Failure is due to principal tension. Okay, so these are the 2 points that you should remember in tension failure in brittle material. And why tension failure is taking place? Because it is weakest in tensile strength only, and maximum tension is coming here. Okay. Okay, very good. So if I want to see the tension failure, so this failure plane will look like this. This will be a rough 90 degree failure. Okay. So failure is happening because of principal tension. Now let us see compression failure of a ductile material. Now just imagine if I take a ductile material, let us say a mild steel I am taking, and on this mild steel specimen I am applying a compressive loading. So P load I have applied. Now because of this P load, what will happen? Since this is a ductile material, it will not crack, or it will not form any rupture surface right away. What will happen? It will undergo large strain again. Okay. So when I apply this loading, it will keep on compressing, and when the longitudinal axis, this dimension will be decreasing, what will be happening? Lateral dimensions will start increasing. And when I'm applying compressive loading, the machine plates will be there, and because of friction between those plates, machine plates and the specimen, because of that friction, it will not be allowed to expand from here and here, but it will be expanding from middle. Okay. So the the specimen will look something like this. The specimen will look something like this. Okay. So lateral expansion will be taking place, and longitudinal compression will be taking place like this. Okay. So this failure will be because of yielding. Okay. In this type of, in ductile material, while we are applying compression loading, there will be no fracture surface. Okay. There will be no fracture surface. This failure will be because of yielding of material or excessive deformation. Okay. So failure will be because of yielding. There will not be any fracture surface. There will not be any fracture surface, and this material will form the shape of a barrel. Barrel, you know, that containers to store liquid, that wooden containers to store liquids, okay, wine and all those kinds of liquids, they were used to store these liquids. So these are called as barrel shape, okay. So the failure specimen will form barrel shape. The failure specimen will form barrel shape, okay, right. Okay, so if I have to see the specimen, this will be the specimen. So this is the original specimen. After some loading, it forms like this. After increasing the load further, we'll see more reduction in longitudinal direction and more increase in the lateral dimensions, okay. So this type of shape is called as barrel shape. Barrel shape, okay. So this is the third type of failure, compression failure in ductile material. Now what will happen if I apply compression in brittle material? So when I apply compression in brittle material, what will happen? Brittle material, although it is weakest in tension, so sometimes what will happen, tension failure will occur, sometimes shear failure will also occur, okay, because their tensile strength and shear strength are not very far away, okay. Tensile, it is weakest in tension, okay. Compression, sorry, brittle material is weakest in tension, but failure will be sometimes happening in shear also, sometimes failure will be happening in tension also, tensile also, okay. So many a times in concrete cubes, while testing, you will see that failure plane will be like this. While doing compression testing of concrete cubes, you will see some cracks like this, and sometimes, many a times, you will see cracks like these also, okay. So these types of cracks, these are forming at 45 degree. When these are forming at 45 degree, that means they are because of shear. And when they are longitudinally like this, these types of cracks, when you will see, they are because of tension. Okay, they are vertical cracks. Okay, so sometimes you will see cracks inclined at 45 degree. These will be because of shear. Sometimes cracks will be at 90 degree. These will be because of tension cracks. Okay, so it is very difficult to tell in a brittle material that which type of failure will occur, but mostly we'll consider shear failure, okay. Mostly we'll consider shear failure. If this question comes in examination, you have to answer shear, okay. In examination, you have to answer shear, right? Okay, so here at 45 degree, the failure plane will be like this, or sometimes the failure plane will be like this also, okay. This will slide like this, okay. So when we are applying compression failure, this will be the failure surface. It will be because of shear, okay. So compression failure in brittle material, failure plane is at 45 degree, failure plane is at 45 degree, and failure plane is at 45 degree. Failure is because of shear. Here also, see, you will be having doubts, sir. It should fail in tension. See, it is practically observed that when we apply loading on very small part, compressive loading, when we apply on very small part, okay, small area, then it will be primarily tension failure. But when we apply compression loading on entire area, then at because of that there will be shear failure, okay. So this is observation. So what happens sometimes when we do compressive testing on concrete specimen, what happens that because of this being rough, not perfectly straight, what happens, some parts are loaded and some areas are unloaded, and because of that there will be some tension loading, okay. So it is observation based, not some theory or some law or rule is there, okay. This is just observation. So don't go too much deep into this. Just remember, when this type of failure comes, you just remember that it will be a shear failure, okay. In examination, just mark shear failure, that will be fine, okay. So the failure surface will be like this. You can see this is the longitudinal axis and this failure surface is going at some angle, Okay, clear? So this is the shear failure. Okay, let's move on to the next one. So next one is torsion failure in ductile material. So we are having ductile material and let us apply torsion. Now ductile material we cannot take just like that any ductile material. We have to take a specific shape, shaft. Okay, we'll take shaft. Now let me first draw the shaft, because when we apply torque only on shafts. Okay, when we apply torque on shafts only. No any other cross section is used for torsion. Okay, so this is my shaft, this is my shaft. Okay, so this is fixed here, shaft is fixed at one end, and on the other end I am applying some. Okay, so when I'm applying some torque here, what will be happening, this is the, let us take this element at the surface, because of torsion there will be shear stresses, and shear stresses will be maximum at the surface only. Okay, the distribution of shear stress because of torsion is like this. Okay, so at the center line there will be zero shear stresses, and as we move away from the center towards the surface, at the surface we will have maximum shear stress. Okay, now because of this the element will be experiencing shear stresses something like this. Because of this element will be experiencing shear stresses something like this. So at this plane, at this 90-degree plane, we will be having maximum shear. So because of this maximum shear, this ductile material will fail in shear itself. Okay, ductile material is weakest in shear. Ductile material is weakest in shear, and shear is coming at this 90-degree surface. Okay, so failure plane is at 90-degree. I am drawing this curved line, but when you see from see, it will be, when I draw a straight line, a circle, on this curved line, on the surface of a cylinder, this curved line will look like this only. Okay, when I see from some angle, it will be looking like curved line, and when I see from straight like this, it will look like a straight line. Okay, so from this angle it will look like this. Okay, but from other angle it might look like straight line also. So in some books you will see that they have drawn straight line, in some books you will see that they have drawn like this. Just like earth, on this earth, if I draw curved line on the surface, so on here it will look like this, but if you see from here, in from front, it will look like this. So this is also not a straight line, this is a curved line, but it looks like a straight line. Okay, similarly with this case. Okay, they all are curved lines only because this is a solid shaft. Okay, cylindrical shaft, right? So the failure will be at here, and failure plane is at 90-degree. Failure plane is at 90-degree, and also there will be a smooth failure surface. Okay, so write down failure plane is at 90-degree. Failure plane is at 90-degree. 90-degree. Failure is because of shear. Failure is because of shear, and failure plane is smooth surface. Failure plane is smooth surface. Failure plane is smooth surface, right? So failure will be at this. So how the failure will look like? So this is the shaft, and if I have rotated like this, so shear will be coming on this plane. Okay, 90-degree plane, and it will be failing like this, right? Okay, so this was the fifth one, and last case, torsion failure in brittle material. Now again I'll draw a shaft. Again I'll draw a shaft because we apply torsion on shaft only. Now this shaft is brittle. This shaft is brittle on brittle material. So just remember, brittle material is weakest in. Tell me, brittle material is weakest in what? So brittle material is weakest in tension. So when brittle material is weakest in tension, then this will fail in tension only. So this is my shaft. Okay, I will apply torsion here. I have applied torsion like this, and the element, failure surface element, yeah, whatever element, stress element will be like this. So here we are having shear, here we are having complementary shear, here we are having shear, and like this. Okay, now here we are having maximum shear on these planes, this plane, this plane, this plane, this plane, all will be having equal shear stresses. But this is weakest in tension. So when this is weakest in tension, at what angle we will be getting tension? So if we draw the element, what we will see that because of this shear element, the tension will be at 45 degree from here. At 45 degree, the resultant of these two will be giving tension like this, okay. And this tension, this maximum tension is on the surface only, not inside. Okay, so there will be a line like this on the surface, like this. Okay, so on the surface, suppose this is the shaft, so on the surface this line of maximum tension will keep on connecting with other cracks, small cracks will start happening, and then this line will keep on getting longer and longer. So there will be an entire surface created like this. So that surface will be at 45 degree, and this surface, shape of this surface will be helicoidal. So this will be a helicoidal surface, rough surface, and it will be at 45 degree. This surface will be at 45 degree. Okay, so failure plane will be a rough helicoidal surface. Failure plane will be a rough helicoidal surface, at 45 degree. Okay, then the failure is because of tension, diagonal tension. The failure is due to diagonal tension, right? Okay, so the failure surface will look something like this. Okay, this is the rough helicoidal surface, okay. So this is forming an helix type of shape. Okay, helicoidal surface is this type of surface. It is at 45 degree, it will be a rough helicoidal surface. So you can see from these two images. Okay, so these were the different types of failures. I hope you understood this and enjoyed the lecture. See you in the next class. Bye bye, take care.